But just have a think about, just have a guess of what you think the distance the Earth to the Sun is in kilometers, and also guess the mass of an oxygen atom in grams. You don't have to write it down anywhere. Just take a second to think about what you might think those answers will be, and we'll come back to them in a moment. All right, so we've only got a few slides to go through. As I said, we're looking at indices and standard form. I can guarantee, as year nines, you guys have definitely done index laws. I'm not sure about standard form. Some of you may know what standard form is. Some of you might not, but we're gonna learn it today regardless. So, as a refresher for index laws, these are all the sort of main index laws that you have probably come across before. I'm just going to do a couple of examples just to refresh our memory on them. So when you're doing index laws, you'll notice that in each of these general examples, I've used the base number as A. So the base needs to be the same number. Or in this examples, we've used X. So say if you had 5 to the power of 2 multiplied by 4 to the power of 3, you can't really simplify that unless you actually work them out. So that base number needs to be the same. Keep that in mind. So if we're doing x squared times x to the power of 3, we can use this index law, and all we have to do is add the two indices together. Get x to the power of 2 plus 3, and we know that 2 plus 3 is 5. This next one is an example of these two. These two are actually essentially the exact same rule. We should know that a divided by sign is the same as sort of putting it as a fraction. These two things are the same. And what we end up with is if you have x to the power of 4 over x to the power of 2, you just need to subtract the powers. So we have x to the power of 4 minus 2. That equals this one is essentially the same thing. You know what? Fractions are actually a bit tricky. So what we'd end up having is x to the power of 1/2 minus 4/5. And subtracting fractions are a bit frustrating. So I might just leave it as that for the moment. This one is a bit different. Is looking at, which one are we? Yeah, this index law. So it might look a little bit different to how you've seen it before, but if you have, oh no, sorry, this one. They're similar. If you have a, say, to the power of m, and if you have that in brackets and the whole thing is raised to another power, you need to multiply the indices. You can see here we have x to the power of 3, and that whole thing, it's in brackets and it's raised to the power of 1/2. We just need to multiply those together. So 3 times 1/2 for our power. And if we're going 3 times 1/2, we just end up with 3/2, or 3 over 2. X to the power of 3 over 2. Now this one may be something you haven't seen before, where we look at negative powers, but essentially we're just going to use the exact same rules. Because we've got it as a fraction, we just think of it in the same way. So we're going to have x 4, and then we need to subtract the power that's on the bottom. So what we're doing is subtracting a negative number. And I know we've definitely subtracting negative numbers before. But if we're subtracting a negative number, what we're actually doing is adding it. So 4 minus negative 3 is the same as 4 plus 3. We're going to end up with x to the power of 7 for that one. Just a bit of a refresh index. Now we're going to look at standard form. So we're going to come back to our guesses from the start. Anyone brave enough to have a bit of a guess for the distance from the Earth to the Sun in kilometers? $20 trillion. That is a lot. I can tell you it's definitely a big number. It's not quite that, though. Bad guess, really. It is 150 million kilometers. 150 mil. So, I've got a few private messages. Some people may have already known that, maybe just off the top of their heads. That's not bad. Let's look at the next one. So, the mass of an oxygen atom in grams. Now, this one's going to be really small. Any guesses for this one? 001. A bit more than that. You can get a type out. I've got to be careful here. So it's 0 point, and I'm not joking with this. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 6. That is a ridiculously small number, and it's ridiculous that I'm having to say the word 0 22 times. So this is why we use standard form. If you know what standard, where I'm going with this, but essentially standard form, we use it in maths and also science a lot. We can write these either really large or really small numbers in a really quick way. So an example of how I'm going to do, let's say 10 to the power of 1. We know that 10 to the power of 1 is just 10. And a trick for that is if you have 10 to the power of some number, that's just how many zeros are on the end. So if we had 10 to the power of 2, I know there's 2 zeros on the end, so it equals 100. If I had 10 to the power of 3, we've got 1,000 because there are 3 zeros. But what happens if I go the other way? If I have 10 to the power of 0? Well, instead of having 1 0, I've only got no zeros. And we can also know that 10 to the power of 0 is going to be 1 because of our index laws. If you have any number to the power of 0, it's going to equal 1. What about negative powers? What do we have? What happens when we do negative powers? If you have 10 to the power of -1, we have 0.1. So what's happening is the decimal place is kind of moving over by one spot. 10 to the power of -2, 0.01. So you can see how each time we go another negative power, the decimal place is going over by 1. So if I skipped a few steps and said 10 to the power of -23, what I'm going to have is 22 zeros. I'm not going to count them out. I'm just going to, let's pretend that's 22 zeros. We're going to have 22 zeros there. So if I wanted to write this number in standard form, the way I'm going to write it, I'll just get rid of these. The way I can write it is 2.66. So I take the numbers here that don't have any zeros in them. I'm going to multiply it by 10 to the -23. Imagine if I take this really small number and multiply it by 2.66, that's what we're going to end up with. So that's how I can write this number in standard form. And writing it like that is a lot easier than having to count out 22 zeros. In a similar way, going the other way, this one could be 1.5 times 10, I think it'll be 10 to the power of 8 kilometers. So again, writing 1.5 times 10 to the a lot easier than writing 150. That's why we use standard form, and that's what it is. It just makes writing really large or really small numbers a lot easier. Now, let's do a bit of a skill check. So have a go. Not easy if you haven't done it before, but just have a bit of a crack. So let's try to put these numbers into standard form. The first one is the speed of light. Maybe to make it a bit better, I might just round this actually. Round it to 300 million meters per second instead. So let's see if we can put this number in standard form. And then also, if the Milky Way has 100 billion stars, remember that 1 billion is the same as 10 to the power of 9. And there are also 100 trillion galaxies in the universe. What's the way that we can and how do we write it in standard form? How many stars there are in the total universe? So give you guys a minute or two to have a think about that, and then we'll go through the answers. All right, you may have figured them out. You may have not yet, but we're going to go through them anyway, and that'll wrap up our first WebEx back. So let's look at the first one, the speed of light. So what I'm going to do first here, I'm going to count how many zeros I've got, and that's going to help me determine, I'm going to have 10 to the power of some number, and knowing how many zeros I've got here is going to help me. So I can see I've got 1, 2, 3, 4, 5, 6, 7, 8. So I know that if I've got 8 zeros, 10 to the 8 is 100 million. Now, if I want to get from 100 million to 300 million, all I need to do is multiply that by 3. So if I have 3 times 10 to the 8, that's going to give me this 300 million number. That's how we're going to do the first one. This one is written as 3 times 10 to the 8 for the first one. Second one is a little trickier. So first we've got 100 billion stars in the Milky Way, and we've got 1 billion is 10 to the 9. So in the Milky Way, there are 100 times 10 to the 9. That's 100 billion stars. Also, apparently, one billion galaxies, and the question just tells us here that 1 trillion is 10 to the power of 12. So what we want to do here is, if we've got 10 to the power of 12 galaxies, and in each galaxy there are 100 billion, to find the total number, what we're going to do is multiply that by 1 trillion. Now, this is where we're looking at our index laws. We know how to multiply these indices together. So we've got 100 times 10 to the power of 9 plus 12. We're doing adding because from our index laws, we know 10 to the power of 9 times 10 to the power of 12. We just add the indices together. So simplifying that, we've got 100 times 10 to the power of 21. Now, you might want to stop there, but you might also notice that 100 is the same as 10 to the power of 2. 2 times 10 to the power of 21. And we can simplify that because the base of these two numbers are 10. We can do exactly what we did over here and just add the indices together. So we end up with 10 to the power of 21 plus 2 which gives us 10 to the power of 23, which again, I need another 100. Ah, I've missed that 100 there. Fair point. Okay, I'll add them in then. That's what happens when you don't read properly. You miss things. If we had, that would be 10 to the power of 2 times another 10 to the power of 2. And in total, we would end up with 10 to the power of 25. Yeah. So firsthand, when you don't read the question properly, you're not going to get it right. So make sure you read the question. Yeah, so 10 to the power of 25 is, again, a lot easier than writing out 25 zeros. So that is why we use standard form.